just to continue with this a little bit, there's more on sidechain information to be gotten. There have been a lot of experiments developed. I just briefly jump through them. For example, you can do, instead of this CBCA-CONH type of connection, you can do a TOXI along the whole side chain and then go via the CO and to the NH of the next amino acid. Or you can do this in this CBCA-NH type, where you do the TOXI and then go from the C alpha via the coupling to the nitrogen to the next amino acid, and intra-residue, of course, is a stronger HNCA type connection. All of this gives you more information, but gets less and less sensitive, of course. Yeah. Then on the backbone, or a little bit extending the backbone, you could do an HNCA-HA as a 4D experiment where you have evolution on carbon alpha and H alpha. Or you could do, and this is an important experiment here, you can, that I did not mention before, going by HNCO, CA, CB, and back. When you have a deuterated protein, then this may be the option. Now, I want to rather cover something else to some extent that also has to do with the side chain, and it's about acquisition of aliphatic carbon spectra. And one of the simplest experiments that one can do is an HCCH cozy experiment. So there's no nitrogen involved. It's just connecting directly by one bond from the proton to the carbon, and then a carbon-carbon, one bond, and then to the attached proton of the next carbon. And this is a mixture of these inept type things and evolution period. Actually, this handwriting is not mine. This is original handwriting by Ed Bax, because this is actually, this is exactly what I was talking about yesterday, that you do an inept here and then tag on the acquisition period. But you can always combine this in this constant time thing. And then this is going to the direct attached carbon, measuring the directly attached carbon frequency, and then mix here, transfer to the next carbon, refocus, and then detect the proton there. Now, here's still the result of this experiment. So this is now a 3D where you have 2 proton dimensions and 1 carbon dimension. And here, this is a carbon plane. Because of folding, it's at the same time at 40 ppm, at 60 ppm, and at 90 ppm. And you see, for example, around 40 ppm, this is this isoleucine, I think 56, and you have the connection from the beta carbon, which is the diagonal, to the alpha. Well, it's going via the carbon to the alpha proton that is detected here in this directly the dimension. And on the other side, to the gamma carbons. And you can do the same thing as a TOXI. So instead of just going by one bond, you can mix with DIPSI or other sequences along the carbon chain, and then you may get in the same way, you know, the connection through the entire side chain. For example, here for this lysine, you're going quite far out, beta, gamma, and delta, and so on, isoleucine. And this is again detected on the protons, but you could also do, if you wanted, 2 carbon frequencies and 1 proton frequency. But what I really wanted to mention more about this is that when you look at the proton-carbon correlation spectrum, 1 bond correlation, like an HMQC or HSQC you could do, then you realize it's, first of all, the carbon range is very wide. So here, around 130 ppm, you have aromatic carbons, and this goes up to about 10 ppm for the methyl carbons. So you roughly have a range of 140 ppm. And now there is also a correlation between the carbon shift and the proton shift that you don't see in the NH correlation, but in the carbon-proton correlation you see it. And this is because the shielding of the carbon and the proton, I mean, they're coming from the electron density, of course, in the CH bond, and this shielding is somehow more correlated than in the backbone NH or CO. And where does this come from? Because the peptide, the bond, is more polarized by hydrogen bonds with neighbors, and that varies a lot. Whereas the CH group is less polar and less influenced by other neighbors or so. And so then you really have the electron density by itself and the immediate chemical structure. And so it correlates. And now because of that, so the shielding is coming from the electron density. The coupling is also coming from the electron density. Yeah. And so you also see a correlation in the coupling constants. And for example, here, these aromatic CH couplings, they are around 160 Hertz. H alpha, C alpha couplings are around 140 Hertz. And the methyl proton carbon couplings, they are around 120 Hertz. It's the same thing. Yeah. So the density somehow that is there it's less for the interaction. This is the J coupling. But now, so there is now this problem in a way that this spectral range is so wide. And if you want to sample all this, you need a large sweep width in principle. And so maybe here it's 150 ppm. And a large sweep width means you need to have small increments. The sweep width in Hertz is 1 over the dwell time. Yeah. And so if I want to cover this, I need to make small increments. But what is very important in the acquisition is that you sample your FID for a long time that you get high resolution. The number of increments times the dwell time is the total acquisition time. And this determines what the width of your line is in principle, if the relaxation has not deteriorated the signal before. Yeah? So meaning if I make a small increment, a small dwell time, I need to have a large number of increments. And that in the indirect dimension costs me a lot of experimental time. And now you can do a trick here because it's correlated. So you could actually do folding, fold the spectra on top of each other, reduce the sweep width. And I think here a kind of a reasonable number would be 33 ppm. And then you will see that, for example, this here will fold exactly on this without overlap. This doesn't work in an NH correlation, but in a CH correlation, it works. And by that, I can make the increment larger, and then I need the dwell time larger, and then I need a less number of increments to achieve the same resolution. And now, so you see this here. So this is now just with a 33 ppm sweep width. And actually now you can do the folding in a way that when you fold one time, it gets negative. When you fold 2 times, it gets positive again. And actually this is here not shown in color, but here were the negative levels and here were the positive levels. And these are the folded peaks, and you could very clearly say this is folded, this is not folded, and then they are not overlapping, and this will not cause a real problem. So this trick you can do, but now the folding, whether it is getting negative in the folding or not, this depends on your first order phase correction through the spectrum, yes? And this first order phase correction is directly following from the effective evolution time that your spins make until you sample the first data point. So the initial T1 delay determines actually the linear phase correction, because let's say you start at time 0 at your carrier, nothing will happen. But when you're off the carrier for a certain time, then you get a phase angle. And depending on how much you're off, you're more in a phase angle or less. Yeah? And this you correct by a linear phase correction. So therefore, basically the first order phase in the convention that we use is the initial time tau that the spins spent in the transverse plane divided by the increment T1 times 360 degrees. And actually in the convention that is used in the Fourier transforms, the zero order phase, if there's no other effects, is just minus half the first order phase. So I could calculate the first order phase from this, and then I also know my zero order phase. Now, what I need to understand is how much evolution is happening until the first data point. And look here, for example, in this there's an HMQC it was. So here, this is the carbon evolution period. This is the carbon 90-degree pulse here. Then there is the T1 half period. And then there's a 180-degree proton decoupling pulse. And then there's another T1 half period. And then there's the next 90-degree carbon pulse. So when I have this T1 in the beginning, this is what you set in Bruker, this is D0 or something, this has a certain value. You have this T1 half there, this is definitely the delay, but then you have evolution also happening during the 180-degree pulse. There's a proton pulse that to many orders of precision does not affect the carbon evolution. So it also evolved during this proton pulse, but then also during these 90-degree pulses, you have chemical shift evolutions, because carbon magnetization somehow starts at Z, you apply this 90-degree pulse and you turn, but while you're turning, the spins are already to some extent transverse and they move around during the pulse. And now would be a good exercise to calculate for a rectangular pulse, the effective evolution time that is happening during the pulse is exactly 2 divided by pi times the 90-degree pulse length. So if I want to calculate the initial delay that we call tau here, this would be the T1 of 0 that I have set in the program, plus the length of the 180-degree pulse, that is also clear. And then what I was talking about is the length of the 90-degree carbon pulses times 2 divided by pi. But I have 2 of them at the beginning and at the end, therefore it is 4 divided by pi times this 90-degree pulse length. And with this, I can calculate exactly what the first order phase should be. And now, this whole thing is then also related to flat baseline. And there's a very tight interrelation between the dwell time, this initial delay, the phases that you apply, and actually the first point multiplication of the FID that you have to apply. And I explain this. Now, So here in this paper, this was simulated. These are all somehow properties of discrete Fourier transform. So if you do a continuous Fourier transform, you don't see this really. Yeah? And here what was simulated is the case where you have now a certain sweep width of a spectrum, and you acquired a full spectrum, and you set this initial delay to half of the dwell time, and you calculate a phase correction like I said before. You get a nice spectrum that is all in phase, and the first point was actually multiplied by 1. Now, if you now reduce the sweep width, meaning I increase the dwell time, what's done here, I get folding. And here in this case, so it is folded in a way that this peak moves to this side and it gets negative. It's a 180-degree linear phase correction so that it becomes negative, okay? And now the take-home message from all this paper is that you get flat baselines after the Fourier transform only if your initial delay is either half a dwell time, a full dwell time, or 0 dwell time. And so half a dwell time and full dwell time is easy to achieve. 0 dwell time we cannot really achieve in this HMQC, for example, because you had these 290-degree pulses and there's already evolution happening. But you can achieve 0 evolution in these constant time experiments where you have a refocusing pulse in the middle, and then the initial evolution is refocused, and only after you move the central 180 away, you have chemical shift evolution. Yeah? But only in these 3 cases, you get a flat baseline. In all other cases, something is not so nice. And it's easy to achieve because you have control over this initial time point. So I just want to, give you some simple rules for this. So you achieve only flat baselines if you set this initial delay to either half full dwell time or 0 dwell time, and I wouldn't use anything else unless you're forced to do it. And for the calculation of this initial time, you take all the delays into account, and you need to know that a rectangular pulse has an effective evolution time of 2 divided by pi times the pulse length, a 90-degree pulse. For a shaped pulse, it will be different. Yeah, that is, then you have to really see an integrator shape or so. Now, the first order phase correction is the initial delay divided by the dwell time that you use times 360 degrees. And this could be a plus or minus sign depending on the program that you use for Fourier transform and phase correction. For example, NMR pipe and Bruker, they are inverse in the sign. And then, so for the initial delays of 0, half a dwell time or full dwell time, this corresponds to a linear phase of 0, 180 degrees or 360 degrees. And the contribution to the 0 order phase from this chemical shift evolution that is happening until the first data point is just minus half of the first order phase. But you can have other effects on the 0 order phase. One we talked about yesterday is the Bloch-Sigert shift. So this would be a constant addition to the 0 order phase that you can correct. And this, what I've been talking about, was all indirect dimension, but in the direct dimension, there is all the hardware that may add an arbitrary phase to it, so where you may not have control over it, but it is just a constant addition. But the rest can be calculated. And now for the first point multiplication, in the case of a first order phase of 180 degrees or 360 degrees, you just leave the first point alone of the FID, multiplied by 1. But in the case of a 0 first-order phase correction, meaning that your acquisition has started at time point 0 exactly, you have to multiply the first time point of the FID by a half. Anybody has an idea why that would be? Implicitly, somehow, the discrete Fourier transform assumes that your time points correspond to the integral of an interval of the signal of the time point plus minus half a dwell time. So when I'm at half a dwell time for the initial delay, I have an integral from time 0 till time 1. And for any later time points, I have the same thing, that I just cover an interval of a full dwell time. But when I'm at time 0, then my digitizer measures the signal at time 0. This is what comes in the signal. But the Fourier transform thinks it's the integral of the signal from half a dwell time before 0 until half a dwell time after 0. And because we think that the whole signal is causal, meaning there is no signal before time 0, and therefore you have this factor of a half in the integral that you need to take into account. And then finally, so if you have a 360-degree first-order phase correction where you have set the initial time point to a full dwell time, meaning you have started your acquisition really one step off from 0, then you basically have completely lost information about time 0 when you think about these integrals and so. And so now you do the phase correction, and that brings everything back into phase, but it assumes basically that at time 0, you have 0 signal. And now at time 0, what is the signal at time 0? It's the integral over the whole spectrum. And so the discrete Fourier transform then thinks the integral over the whole spectrum is 0. And how is this achieved? By just shifting the spectrum up and down, such that if, let's say, you have a positive peak, the area under the positive peak until 0 equals the area under all the rest in the negatives on the negative side. Yeah? And so, but this is a constant shift, and that you can correct rather easily by a constant baseline correction. So you have lost information, but you can make up for it. I mean, of course, if your spectrum is completely crowded, then it's a little bit difficult to find, but it's just a constant shift. Okay, so I quickly go through 3D and 4D noses. This is really very quick. We have not talked about the NOE transfer whatsoever. We were talking J J-coupling transfer. And we saw yesterday that it is limited by the T2 because we have transverse magnetization. The NOE transfer, I mean, normally we do it between protons because it's the most sensitive, but this is a longitudinal thing. So normally you would somehow invert one proton relative to the others. You go to minus Z, and then this proton will see the rest of the protein and tries to come back. How does it come back? By fluctuations of the magnetic field that are induced by the rotation, and these fluctuations come from dipolar couplings. And so this is a relaxation effect in the end. And the relaxation rate, or the build-up rate of the nosy is, again, it's a process that doesn't require energy because the protons flip. So it's at spectral density 0, and therefore it's proportional to tau c, meaning for large proteins, actually, the NOE transfer gets more efficient. So NOE is good for large proteins. Then a normal NOSE experiment would look like this. You have a proton evolution period here, and then you just flip part of the magnetization to -z by this pulse, and then wait for a certain time on the order of 100 milliseconds, let the environment bring back your proton to equilibrium to some extent, and by the same token, the environment gets out of equilibrium, and that we detect by the next 90-degree pulse, and basically see it as a difference relative to equilibrium. So this is the NOSE, and now we could try to get more resolved information by combining this NOSE with an inept step to learn about the frequency of an attached nucleus. For example, if you have a NOSE between any aliphatic proton and an amide proton, you would like to know the frequency of the nitrogen that is attached to the amide. So you could use an HSQC, proton nitrogen, and what all you have to do is to get them for a 3D spectrum is put this NOE experiment in front of the HSQC. So this is very easy. And now there's the original experiments. I think most of them, Gottfried, if I forgot one of yours, I apologize. So it's pretty easy. It's basically connecting an HMQC or HSQC to a proton evolution period, and in between you have an NOE mixing period. What is very similar in the setup is actually to connect a proton-proton toxi and then detect the heteronuclei that are attached to it. So it has a 15N separated 3D toxi on the protons. And here this is just some pulse sequences that I sketched. I mean, you can take any of the good HMQC, HSQC sequences and just put an NOE NOSE experiment in front of it, or a toxi. Now, this is kind of a little bit asymmetric now, because you have one proton where you only measure the proton chemical shift and nothing else. Do the NOE to the next proton, and then measure the frequency of the attached heteronucleus in this HMQC, HSQC type of experiment. But it would be nice eventually to know also the frequency of the heteronucleus that is attached to the first proton. And so you could do a 4D experiment, like, for example, an N15 edited and carbon edited 4D NOSE. And of course, what it does for you is to give you more resolution, more information. I think here is some sequences. So this part here, this may be better replaced in the end by this Watergate thing. But the outcome of it is now the following. So here on the left side, you have a strip from a 3D NOSE and 15 edited, this interferon gamma. On the vertical axis, you have all the protons that interact with the amide proton of asparagine 17. But you don't know what is the carbon frequency of the attached aliphatic carbons. And if you look at the plane from the 4D C13 and 15 edited NOSE, then you pull out these frequencies in a nice carbon plane as well. And this may really help you for assignment. The same thing can be done with carbon-carbon edited NOSE. All the problems are coming because, of course, you need more increments. This takes more time. Sensitivity is getting lower, but it can be really quite, I mean, astonishing how much more resolution you get here. So this is a paper by Marius Clor, and you see here, for example, this is a plane from such a 4D carbon-carbon NOSE, And the region here is enlarged here, and this is the signal that you would detect in a normal 2D proton-proton nosy experiment. Yeah. But it's limited in sensitivity and in resolution. For smaller proteins, when you're not limited in sensitivity, you may overcome the resolution problem with noose sampling or so. But for larger proteins, I think sensitivity is always the problem. So now I want to add a few other small or not so small things for enhancements of sensitivity and resolution. One of them is deuteration. Most of the relaxation that is happening is from dipolar couplings to protons. They have the largest magnetic moment. When you replace the protons by deuterons, deuteron magnetic moment is a factor 6.5 smaller than the proton magnetic moment.
So the dipolar relaxation is?
First magnetic moment times second magnetic moment squared, divided by r to the 6. So if I replace the proton by a deuteron, I get a factor of 6.5 squared less in the relaxation, but it's not completely true because there's also still the size of the spin coming in. So in reality, I think it's 8/3 of 1 over 6.5 squared. So it's about 1 divided by 16. In reality, we have never seen this because of other things still happening, like dynamic frequency shift and what have you. But so in practice, certainly a factor of 3 to 4. And you can see this here. This is it's a triple resonance experiment, but it's the carbon plane here. And this is for the protonated case. And this is for the deuterated case. And so this is C alpha region, and the C alpha FID is sampled so long that you can resolve the C alpha C beta carbon splitting. But what you realize is that in the protonated case, it's not really well resolved because the signal has already decayed when this develops. So C alpha C beta splitting is about 30 to 35 hertz. This means your signal is modulated with a cosine that has a zero crossing at 1 divided by 2 times 30, means 1 divided by 60 is roughly 15 to 16 milliseconds. So when you look at this carbon FID, it will oscillate with a cosine modulation that has a zero crossing at about 15 milliseconds because of the C alpha C beta carbon coupling. But in the protonated case, you have the relaxation happening in addition, and then the signal has almost decayed and you hardly resolve the splitting. But in the deuterated case, you can nicely see it. There's, by the way, another effect. This is not an artifact. It's not a problem of the chemical shift referencing, but you see that in the deuterated case, the carbon resonance is shifted upfield. Any idea what this is? Isotope shift, yes. So this is used in many multinuclear sequences, of course, and certainly in the TROSY sequences. So this is the effect on T2, but there's also an effect on the NOE, because in a protonated case, so when you make an NOE transfer, you start on 1 proton, but then you have nearby protons and the magnetization goes to the nearby protons. And when you have an extended mixing time, then from the nearby protons, it again goes to other protons. It's what you call spin diffusion. And if you have another proton that is further away, you hardly detect any NOE anymore because the magnetization has spread out everywhere. But when you dilute now the proton spins with deuteration of the aliphatic groups and back exchange, for example, the amides, then the magnetization does not go very much to the deuterons. And then when you have a longer mixing time, you will get much more magnetization onto a faraway proton. And this works pretty well, actually, between amide protons with a mixing time of, let's say, 200 to 300 milliseconds on a deuterated background. Then you see not in alpha helices, you always see NOEs, but you see across the beta sheet and up to maybe 5 angstrom easily. So this is the effect of the deuteration. Then before Trosy, Louis Kay and Art Palmer had the idea. I talked yesterday about the sensitivity loss that you get when you add an additional dimension, because you need to acquire in the additional dimension the X and the Y component of the signal. And what these people then found is that when you add this additional sequence, you can at the same time transfer magnetization from the X and the Y component onto the detected proton magnetization, and that gets rid of this square root of 2 loss in sensitivity. But of course, you add additional delays into the sequence, and you know that this costs you relaxation. And I think this is from the K paper. They were honest enough to tell you that you lose the signal. And so this is the signal to noise as a function of the correlation time or the gain that you would have. And so they say that about 30 nanoseconds, you actually are losing signal again, but before you gain. So this was before Trosy, but now the much bigger enhancement you get from the Trosy. And I don't want to explain much about this, but the basic figure is this one. So if we don't decouple in a HSQC, proton nitrogen HSQC in both dimensions, you will get a splitting of the peak into 4. And one of these 4 peaks, this one here, relaxes with the difference of the CSA and the dipolar coupling squared. And the other one here, this relaxes with the sum of the 2. One gets much broader, but this one gets narrow. And that you can do by also this kind of transfer in a way and get sensitivity enhancement and resolution enhancement. And this is put into these backbone assignment sequences here in this paper by Salzman and colleagues. Now, one thing just to be quantitative about this also. I talked yesterday about the fact that when you have a longitudinal proton magnetization during your protein sequence, we had NXHZ as a term. This HZ will make NOEs to other protons and thereby relax. And the same thing happens in the Trosy sequence. Now, in the Trosy sequence, you are interested in the proton H alpha state. When the nitrogen is transverse, you want to keep this in the H alpha state. And this is a kind of a proton polarization. But this proton polarization will again make NOEs to nearby protons and will be relaxed by this. And so what you need to reduce this effect is deuteration again. And this was here checked by this paper by the Beck's group. You see, for example, this is the Trosy T2 measured by spin echo. You see that in protonated ubiquitin, it's on 800 megahertz, 111 milliseconds, but the deuterated is 200 milliseconds. So if you have protonation, it's not very good. So you really need deuteration. Otherwise, you lose a lot. And this is what for this enzyme 1, it's the same thing. So this is about TROSY. Then another thing that was developed by Roland Rieck and colleagues, actually
Claudio
Dalvid had a similar idea even before, is to use just relaxation to transfer proton magnetization into antiphase magnetization with respect to the nitrogen. And for that, you have to know that when you talk about transverse proton magnetization like this HX, it's actually consisting of a term that is HX N alpha plus a term NX N beta. And these two terms, with the nitrogen up or down, they have different relaxation rates because of this CSA dipolar cross correlation. So actually, this term relaxes faster, the beta term, than the alpha term. So all you have to do is make transverse proton magnetization and wait for a certain time. Then this one has decayed, and you're left over possibly only with this one. And this is a sum of HX magnetization and antiphase HX and Z magnetization. It's used in the script for very large proteins. I don't have much experience with this, but it's an interesting approach. And then one other thing, we talked about this yesterday also already, that the water has a T1 of about 4 seconds when we work with water. And now in your pulse sequences, when you try to get rid of water, you may use gradients where you dephase the water. And if you have dephased the water, if you want to come back to equilibrium, it needs to come back via the T1. And it will take 4 seconds, or maybe better 12 seconds, 3 times T1, until you're really back to equilibrium. Now, you want to pulse normally at 1 or 2 seconds maximally between 2 experiments. And so when you do this, then your water will never be back to equilibrium, and you're basically attenuating the water signal. This would not be a problem, but the water is actually exchanging magnetization with your protein directly via hydrogen exchange, and also indirectly via dipolar exchange. And so when you attenuate the water, then you will attenuate the magnetization of your protein protons that are in exchange with water. And what you can do is now to avoid this situation and try to keep the water more or less at its equilibrium position. You could, for every hard pulse that you apply on all the protons, make a very weak soft pulse on the water that reverses the action of the hard pulse. So for example, if I have here a hard pulse 90° X on the protons, then I could precede it by a soft 90° minus X pulse that only excites the water, and the water will have 0 rotation. And so it will stay along the Z-axis if it was before on the Z-axis. And then here, this element is actually element of a Watergate sequence where you have a 180° hard pulse, and it's preceded by a minus 90° soft pulse on water and followed by a minus 90° soft pulse. And the net rotation on water will be 0. And by that, also the water stays along the Z-axis. And this is implemented here in a way in this water flipback HSQC. And you can put this into many, many other sequences. Now, you see the effect here. So this is calmodulin at pH 6.6. This is still actually moderate exchange with water. You know that the hydrogen exchange with water is acid and base catalyzed. So when you go to high pH values, it gets faster and faster. And you see here, this is now an HSQC with water scrambling, where you kill the water. And here these resonances N42, S81 or so, D78 are hardly visible. But when you do the water flip back, you get a lot of the intensity back. Maybe one other thing I should explain for the water still is, so the water T1 is about 4 seconds. What about T2? Have you ever tried to measure water T2? No. Have you ever looked at the FID of water alone? How fast does this come back to equilibrium? Or how fast does it disappear? Let's put it that way. Then it's very fast. It's radiation damping that brings it back very, very quickly. Yeah. So you have 110 molar of protons in water, no? And so this is a huge signal when it's in phase in one direction, and this makes a strong magnetic moment. When this rotates, it makes a strong current in the coil, and this coil makes again a magnetic field that interacts with your magnetic rotating moment. And with the cryoprobe, the coupling to the coil becomes more efficient, Q, and so, and then of course this effect is more efficient, so can be only 5 milliseconds, something like this now. It's not 4 seconds, definitely. Also on a normal probe, maybe on a normal probe, it's 50 milliseconds to 100 milliseconds maximally. When you detune, it becomes longer and longer. No? So if we didn't have this radiation damping effect, and you would try to measure the water T2 in a proper way, so if it's pure water, how long would it be? It should be the same as T1. No, I mean, small molecules, the T1 and the T2 is the same. So I think I have never measured it on pure water. But now when you add biomolecules to your solutions, there's something else happening. Exchange will do a lot. And basically everywhere you have OH groups, and the OH groups exchange very effectively with water. And that will bring your water T2 down by exchange. Yeah. Now, I think I've just put here together some kind of a sensitivity estimate of these different experiments. The HNCO is the most sensitive one that you can do. And people often don't do it because it doesn't give you connectivity information, but for getting an idea how many resonances you can observe and to have dispersion and for sensitivity, it's the best. And so if you have then, I mean, all the others, then HNCA, of course, gives you connectivity information. And yeah, here's a question: if you have deuterated proteins and then this HNCA-CB experiment, they are probably the best to get you connectivity information. Now, another small remark about how many dimensions you want to acquire. This is actually about the CBCA-CONH experiment, because one could do the CBCA-CONH experiment in a 4-dimensional way, where you detect the beta proton, beta carbon, the NH of the next amino acid, so in 4 dimensions. Could even do 5 dimensions, recording the CO also, because this is all on the pathway. It doesn't cost anything for the transfer. But then you have to think whether it really helps you for anything. And in most cases, it doesn't help you. No? So with every additional dimension, you usually use a square root of 2 in signal to noise, unless you implement this Ran's K trick. And then if you have additional transfer step, like in the HNCA-HA relative to the HNCA, then you also lose, of course. you have a resolution loss almost always, because let's talk about this HB, CB, and H experiment. For example, I could do it as a 4D with 8 complex points in H beta, 8 complex points in C beta, and then these points in N15 and proton. But in the same time, so this is 8 complex points is 16 real and imaginaries. So it's 16 times 16 increments, 256 increments. In the same time, I can do 2 3Ds with 64 complex increments, let's say in H beta, which is 128 real and imaginary increments, and I can do 64 complex increments in C beta. So I have 2 3Ds in parallel with many more increments and possibly higher resolution. So more dimensions are useful when there is overlap and you can resolve the overlap, and the higher dimensional spectrum is not limited in sensitivity or resolution. For smaller folded proteins, I think these CBCA-CONH type experiments as 4Ds are not useful. They may be useful for unfolded proteins where you're not limited in sensitivity because the relaxation is so long. And then Louis K. assigned this 700 residue protein. They had to use these 4D experiments. And in 4D noses, sometimes useful, but I think sensitivity can be a problem. In most cases, is a problem.